First, a brief introduction from Angjoo. She's a professor in ECE at the University of California at Berkeley. She's also a research scientist at Google Research and serves on the advisory board of Wonder Dynamics. She obtained her PhD at the University of Maryland and then had a postdoc at the Max Planck Institute in Tübingen and then at UC Berkeley. She received the Best Paper Award at Eurographics 2016. She's interested in general in building a system that can capture, perceive, and understand embodied agents in the 3D world from everyday photographs and videos. And I'm looking forward to see her latest ideas.
All right, thank you so much for the introduction. I'm happy to be here. It's very nice to see everyone's faces, although I hope this is our last virtual conference. Okay, so let's dive in. I'm talking about NeRF, which is perfect because Jitendra also covered this, talked about this. And in particular, I'm talking about making it real time. And the point that I'm really excited about is that this really enables us to do visual debugging, which is very important whenever you're doing any of these things. Okay, so let's just dive in. There's such thing called NeRF that you may have heard, which can reconstruct these synthetic scenes or real scenes with very photorealistic content. I'm sure people in this audience have an idea, but let me just go over it in a minute. Which is that NeRF is a coordinate-based neural networks that takes in X, Y, Z and the view directions, phi and theta, which is supposed to be 2. It takes in 5 things and outputs color, RGB, and the density. And how you train this is that you have many pictures of the scene. So in each of these cameras have a picture associated to it. From each of these pictures, you shoot a pixel, you shoot a ray in the scene, and then ask these coordinate neural networks, like what is the density and the color at that particular point, which you can actually just integrate using this volumetric integration function, using this transmittance in alpha, which is a function of the density. You do this for many different views and you optimize, fit this network to a single scene. Because of this, you actually have to have all of these images with the known cameras, and then optimize the NeRF, which allows you to visualize the scene from many different viewpoints. And as you know, there's been a lot of work in this domain with lots and lots of follow-up works. Okay, and it's partly because it's really gives you really beautiful scenes, and also, but then also there is a lot of limitations. So this is a slide credit to my student Matt. There's a never-ending list of NeRF limitations. It's slow, it's so to train and to render, and all of these things, which, you know, a lot of the groups have been working on. And in my work, in my group, we looked at how can we make NeRF generalized to few shot scenarios with pixel NeRF. And today I'm going to talk about how to make it real time. But before I talk about this, I kind of want to address, like, why am I doing this? Why are we doing this to begin with? Like, why is this line of work really exciting to us in my group? And I think that is one, is that volumetric rendering is a very, very effective differentiable renderer. So here I will show you the visualization of the NeRF fitting to memorize this scene with this chair. Of course, you have like hundreds of images, right? But this is the initialization. And when I play the video, did you see how quickly this is how quickly the network basically got to the rough shape, right? This is the depth it's being visualized. But let me redo this video again, okay? It really converges very quickly to the rough shape. And then it takes like, has a very, very, very long tail to get the high frequency details. Okay, but this fast convergence is a very nice thing when you want to learn from images. And compared to other differentiable renderers that I've worked with, like meshes, for example, it has a lot wider basin of attraction. And I think this is really nice. And this is also very key for 3D learning from images without 3D supervision, which I've been looking at a lot. And this is the theme of this workshop. Okay, so number one is this. And the second thing, which is that is a really compact way to model the Plenoptic function. And I really like this viewpoint in thinking about what NeRF is what, okay? So let's remind ourselves, what is the Plenoptic function? Okay, so Plenoptic function is a conceptual, psychological experiment to think about what is the set of all things we can ever see at any point in time. Okay, and this was the answer to this question was the Plenoptic function by Adelson and Bergen in 91. But let me give you an example. Okay, so let's start with a simpler case where it's a stationary person like this in the world, and we want to parameterize everything that they can see. Okay, so what is this function? This function is a function that takes in phi and theta and phi for the viewpoint, and wavelength, lambda for the wavelength. It models the intensity of light seen from a single viewpoint at a single time at this specific point as a function of wavelength. So it can basically describe every single thing this person would see at this particular moment. Okay, now you can generalize this to wider stuff. So let's start adding time and location. Then you're going to get this 7-dimensional function where you have the viewpoint, which is a direction, the wavelength, which for the color or the actual wavelength is a physics-based model, everything, time, and then also 3D location. So this is now why you see these like many different spheres at every single point. Okay, and this function can reconstruct every possible view at every moment from every position at every wavelength that anyone has ever seen it. It's the entirety of our visual reality. It has every photograph, every movie, anything that people can ever see. This is crazy. This is a crazy thing. Teaching is really good because I've heard about this multiple times. It didn't really click until I started really teaching what this was. This really is like a model of everything that we can ever see for the virtual reality. Of course, we don't know how to parameterize this function. This is a very, very expensive, large function, right? Like you can think of the street view as an example because they've captured, like a 360 image at every single point, which is like a sample of this space, right? So you could think of this function as like a very big lookup table with the street view. But what am I talking about? Why am I talking about this? I'm talking about this because let's just kind of like remove some of the stuff in here. Okay, so let's just not worry about time for the moment. Let's get rid of the wavelength because we can output color. Okay, so then you're actually going to get something like this, which takes in viewpoint, phi and theta and phi, and then the location, vx, voi, vz of this little sphere. And does this look familiar to everyone? And I think it should look like NeRF is what I hope everybody's thinking about. Okay, and so basically NeRF is modeling this plenoptic function. And in a very compact way with MLP. Okay, obviously it's not for every single moment because it's we can only currently optimize for this a specific scene. But I really think this picture is very important to have it in mind of what is NeRF actually doing, because you have these points and you're modeling the viewpoint at every single point. Okay, and I think this is really okay. Well, we're gonna come back to this. And of course, when we talk about plenoptic function. We can't talk about light fields or lumigraphs, which are also SIGGRAPH 1996 paper. So SIGGRAPH 1996 is a very good year because that's when Paul Dubovic's the differentiable stereopsis or the stereopsis paper came out also. And also that's when the light field and the lumigraph papers are also there. But the light fields are essentially a 2D slice of this plenoptic function, as opposed to NeRF actually can, in theory, can model the entirety of it. You can actually model through occlusion inside. So that's kind of a difference. But anyway, I just want you to keep this picture in mind, and we're going to come back to this. Okay, so with this in mind, let's talk about how to make this fast. So first, I am going to start with the demo. So here is a screen capture of us rendering these synthetic scenes in NeRF. In real time. You can see these view-dependent effects. And one thing I want to say now is that you can convert your existing NeRF to this format, which allows you to do these visualizations for visual debugging, which I think is the most exciting part. This visualizer also has these kind of, you can insert objects in this, you can change the viewpoints. Actually, I'm going to try this we have a browser demo. So the first author, Alex, built this really nice demo. So let's go try it out. All right, so I'm going to try it with the hot dog. Can you see my screen? I hope you can see my screen. Yeah. Okay, good. Okay, so here is the hot dog. And so you can look at the hot dog right now I have to do zoom and this, so it might be a little bit slower than normal, but like you can do this and you can slice the scene. Like, if you're ever curious about what the hot dog looks like from inside, you can take a look. You can also visualize the kind of to fix the viewpoint, but change the viewpoints of this to figure out what kind of like view dependence effects that this network is learning, or this final result is learning. And this is like the data structure in which we fit this, and we can add all these things, so you can play around with this. And later I will show that you can also convert your model to this format, so you can actually do visual debugging on your own NeRF that you're developing. All right, so let's think about, before I talk about how to make it fast, let's think about why is NeRF slow to begin with. Okay, so NeRF is super slow to render, and rendering this 800 by 800 image takes about half a minute, even on a very high-end GPU, because it requires, you need to sample this whole space and then query your neural network every single time. And this is, you have like 122 million calls, and this is what makes it really slow. Okay, so the number one reason that it's slow is because of this sampling necessary. So for every single image that you want to render, for every single pixel, you have to shoot array in the world, and for every single sample, for every single viewpoint, you have to actually ask this network what the color and the density is. Okay, and so you have to sample densely in this R5, or more like R3 first, which is the expensive part. Okay, but for the figuring out where the density is, you can think that how do you actually make things fast? Well, fast rendering usually relies on caching. Okay, so you can just think that for the density, you could just cache where the high density areas are, so you don't actually have to. You can pre-compute this, and you don't have to ask empty points, empty locations, what the network is, because that is empty from the pre-computation. Now, that idea of caching is a rather tricky to apply because of this view dependence, right? If it's just the density, you can cache your voxels, sparse voxels, but R5 is a lot to cache. Okay, quickly goes up. So that's really the view dependence is kind of like making it very difficult to just caching it, okay? But this is where I want to think about the plenoptic functions, okay? So let's recall this picture. This is what what we're trying to model anyway. So from this picture, you can already see that you can factorize the location of where these spheres are placed, and the view direction, which is what does that scene look like from all different viewpoints? What is the light that is being delivered to the center of the sphere from very different locations? And so you can actually factorize this. So this is really the kind of insight into how, like, a lot of the how we make this NeRF real time. So the high level idea is that we're going to take the original NeRF network that is small, and we're going to apply some magic that factorizes the location and the viewpoint, view dependent effects and the location of these densities. If we do that, we can actually pre-compute, pack this in a pre-computed representation that we call PlenOctree, because we're inspired by the Plenoptic function. But it really is that picture that we just saw, which is that we're going to store these spherical functions sparsely in this grid, which is kind of what Plenoptic function is kind of modeling. Okay, so that's really the big picture. All right. Okay, so our approach relies on two steps. The first step is to factor out the view dependency, and this can be done in two ways, and this is why you can actually convert an existing NeRF to that, or you can train a NeRF from scratch. Okay, so the point is that we don't want this second network call. It's annoying to do and makes it hard to cache. Well, there's a nice thing called spherical functions. Spherical functions is just a function defined on a sphere so that you can query any viewpoint and get a color out of it. A representative function like this is that of spherical harmonics, which allows you to compute these things. But that's not the only spherical function. You can use any spherical function. But the idea here is that we're going to replace a NeRF to, instead of outputting the color after given direction, we're going to make it output k coefficients of the spherical harmonic basis. Okay, so spherical harmonics models the spherical function like a Fourier basis. So basically, these are different bases. Oops. So these are different bases, like these pyramidal things that you're going to see are different bases, and you're going to output the coefficients, which get multiplied to these bases, and then you take linear combination of this, which gives you the spherical function that you can actually update. Okay, so the moment you have these 9 coefficients, at this time, what you do is you get the view direction. This gives you the analytical basis. You can compute this, and then you just take linear combination of this to get the color that you want. You could have used other spherical functions like spherical Gaussians or anisotropic spherical Gaussians. We actually played around with the spherical Gaussian and found similar performance with spherical harmonics. Other works, you could also learn a basis function on your own. This is what the fast NeRF does. But once which is a concurrent work, but once you start learning basis functions, that basis function is very specific to that scene because you're always overfitting to the scene. The nice thing about spherical harmonics or the spherical Gaussian is that you're having a central global basis for all possible scenes. So you don't even have to, cache these bases either. Anyway, these are just numbers showing that spherical harmonics, spherical Gaussians gave pretty similar results. And so the rest of this talk, we're just going to go with spherical harmonics. Okay, so you can train that spherical harmonics NeRF from scratch. But sometimes, you just want to, for visual debugging, you might have your own NeRF and you want to you want to change that. So in order to do that, what you can do is you just take your NeRF, just sample at every single point, many different view directions, and try to estimate the coefficients of the spherical functions, for spherical harmonics, by just solving least squares. So you can also do Monte Carlo integration, but we have this implemented, and so you can just take your network and then do this. And obviously, the quality depends on the number of samples that you take. But even in like a minute or so, you can get reasonable one if you just want to do visual debugging. So you can always project your normal NeRF into this space using spherical harmonics. Okay. So now that you do this, then the question is how to convert it to PlenOctrees, which is a view-dependent octree. So what is it? Again, it's a sparse voxels, which means the voxel cell only exists at places where the density is high because we don't want to query empty spaces or store them. And that every single cell, it stores these coefficients. So, so if there's like 9 bases for every single color channel, then you have 9 coefficients, right? So the number of bases also changes the expressivity or the size of this. So here is, I guess, 9, yeah. Okay, and how you do this? You just take your NeRF SH and then you just sample your grid on the resolution of 2n to get the density. You threshold and keep only parts that have high density, and then store your spherical coefficients in the octree leaves. Then, when you render, you can shoot your ray, but now you don't have to render out. You don't have to sample when there's, the cell actually reflects only where things are relevant. So you get to skip a lot of things. So this is really number one, it gets fast, okay? Second, we don't need to query another neural network to get the direction, so it's also fast. And then you just kind of render this like in normal NeRF. Okay, so where's the trade-off, right? Because there's always a trade-off. So the trade-off is usually the quality. So on this left axis, you see the PSNR. Let me see if whatever. And then on the right side is the frames per second. So you want to be as high on this corner as possible because that means you are fast, but then the quality is also high. And later we're going to show how we actually don't need to compromise on the quality because you can directly fine tune your PlenOctree again to get a nice color. But so basically this. And then we achieve like 100 FPS, which is 3,000 times faster than NeRF. Another point is that because we are relying on a caching-based strategy, right? The other trade-off is going to be the file size because the more complex the scene, the more complex you gotta store, and so that really also directly determines the PSNR, the quality. And we are showing these different trade-offs with the storage. For example, like the one that I showed in the demo is like a pretty lightweight one because we want to be able to load very quickly. Okay, all right. So here's some results of the PlenOctree. These are 2 different variants. They both render quickly. And you can change you can have these different various parameters to make it even faster depending on your application. Okay, so a couple of details. Because we actually have to cache this in a sparse voxel or octree, we don't really want your NeRF to have a lot of like junk in the places it doesn't matter. So for the hot dog scene, for example, all the cameras are on the upper hemisphere. Okay, so if you don't do anything, naively train your NeRF actually prepares like a plate for your table for your hot dog to put things in, because if it's all white, it doesn't really care how it models the white solidness. But then if you had all of this chunky white stuff at the bottom, you got to put this in your PlenOctree, and you don't want to really spend your memory storing that. And so we actually additionally train your NeRF with this sparsity loss, which nicely gets rid of these unnecessary stuff. Which is important for smaller file size. So that's one. The second thing is you can actually fine tune the octree values to the training data. There's nothing different once you convert it to the PlenOctree. You just, oops, oh, there's a line from here. So you can see that like this is right after, this is the ground truth. This is right after you convert your NeRF to, after training a while, to PlenOctree. And now you can directly optimize just the values of the coefficients. Okay, the structure is already set to you, so you don't change that. But you can do this, and then you can see like a marginal improvement in the PSNR. You get things get sharper. So this kind of gives you this idea. You can actually stop training NeRF early and then switch over to PlenOctree, which kind of allows you to train NeRF in a slightly faster way. So in this, we are showing the plot of the total time training required and the quality of PSNR. And so you can see how NeRF has this really long, takes a long time to get to high quality results. And the thing you can do is actually you can train NeRF for like 3 hours and then switch over to PlenOctree and do fine tuning, and you can quickly get to these values, higher PSNR. The thing is, you still need to do the training right now. So this really begs the question of like, can you actually just bypass the MLP altogether and directly optimize this? Which is an interesting question that we're asking. But right now, you still need the first, 3 hours of NeRF training to get the octree structure, because that's quite difficult to differentiate against. Anyway, but because of this, here are some results. On tanks and temples, you can see that because we can actually fine tune on PlenOctree after getting the NeRF, we actually get a nicer PSNR on these scenes. And here are some more results on the real tanks from tanks and temples. Okay. All right. Okay. All right. So, so that's kind of that's basically the method and the results. So there are a lot of concurrent works that tries to make NeRF real time. Next is a similar approach, but using MPI as the representation instead of NeRF, and it also uses spherical harmonics to model view dependency, so you can see it from one direction. And then these are 3 other variants that are concurrent in this ICCV. They all kind of basically use similar intuition, but there's a different implementation, so it might be interesting. It's interesting to check them out, and I highly encourage you to do so. But I think ours is the only one where you can take your existing NeRF and use it for debugging, if I understand correctly. Okay, so what's the limitation in future work? So the trade-off really is that you're going to have a large file size depending on the complexity of your scene. And to carry these around for faster, we do a demo on the web. So and then for that, we actually do extra quantization to make it fast to render, to load these parameters. And then as the scene gets large and large, the rendering speed can still get slow. And one of the reasons is this kind of junk that like NeRF kind of likes to put the cloudy things, it doesn't see, it's a Plenoptic function. It models what it looks like. And so it can put a lot of junk that doesn't correspond to any geometry to get the nice color, which increases the size of your, scene and everything. So one idea is to maybe convert it to surface light field like representation, which is also a 2D surface slice of the Plenoptic function. Another thing is that the higher degree spherical harmonics are very pointy. So once you start using some coefficient for certain viewpoints, when you look at it from unseen directions, you might get these like really bright colors, but other basis functions could help on this. And of course, you're going to see these like artifacts when you zoom in a lot. And you could fix this with trilinear interpolation, but then it also gets a little bit slow. Okay, but in summary, basically, we provide this kind of intuitive ideas of how to think about NeRF, where we factorize the geometry and view-dependent effects. This allows us to do sparse voxel caching with explicit spherical functions, and you can get 3000 speed up over OG NeRF, and you can directly optimize the PlenOctree, which is an exciting part of maybe training that pointing to the possibility of making NeRF training faster. And the thing that I'm most excited about is that you can convert your existing NeRFs, which is great for visual debugging. And Alex made this tool, which is amazing, I think. So you can do pip install NeRF viz, and you can install this thing. You can visualize your NeRF that you're training on your browser. You can show these cameras and all of these things here. And then we actually use this in our lab where, we're trying to reconstruct the scene, but it's nice because you get to cut these things out, figure out what the bounds are, which is kind of important when you're doing all of these things. And visual debugging is so important, right? And if it takes such a long time to render every single view, your development and research gets really slow. So I'm really excited about this library. Of course, all of the code on PlenOctrees is also available. So I hope this is useful to everyone. I want to end with a thank you note to my team. And first author, Alex Yu in particular, when he worked on this, he was only an undergrad. And yeah, he built a lot of tools for this. We're going to be in poster session this week, Tuesday to 1 to 2 p.m. and Thursday at 3 p.m. early in the morning for us. So please come say hi and ask any questions. All right.
Thanks a lot, Angjoo. These are really cool results. Indeed, I think there was a question that I think you answered almost throughout the last parts of the presentation. So Andrea Vidal is asking, how would you also speed up the training? And you mentioned you can also optimize the PlenOctree. Maybe I can add a bit on top of that. So can you actually start to optimize directly with some generic PlenOctree and then refine it as you go? And have you tried to go beyond this that you have shown here in this slide?
Yeah, we're trying this, but it's, we'll see how it goes. Maybe we will have some good things, but I think the issue is that the PlenOctree, the space discretization is quite difficult to gradient backprop over. So basically, once you make a mistake, it's kind of difficult to, recover from it, right? Once you say that the perp doesn't exist. So the initialization is quite important. Another thing though, is that the number of parameters in NeRF is much less than the actual space in which it's modeling. So it is doing a lot of compression, right? And so if you directly start doing this in the voxel space, it is also, as you increase your, resolution, you're gonna hit a point where it's completely underdetermined. And this thing can be really, really good at overfitting on your existing views and don't really naturalize to the unseen views. And so I think it's a matter of what kind of regularization can you add in order to, make this a little bit more smooth like this, maybe a coarsify. I don't know, we're kind of trying to look into this question because we would all like our NeRF to train faster. We will see.
Okay, I have another question. So you are converting the NeRF to this PlenOctree. How fast is the conversion?
Yeah, conversion is quite fast. If you want to use it for debugging purposes, you can do it in a minute. The longer you sample, the higher quality your spherical harmonics are going to be, obviously. But with 20 minutes, I think you can take enough samples. And so it's really, you can do it a minute is fine.
Okay, so it will give you enough resolution to work with. In a minute, you will get enough resolution to work with the renderings.
Yeah, you mean to do your visualization. Yeah, I think all of these visualization that we do is you don't it's really especially I think whenever you're doing visual debugging, I think a lot of it is about the structure, then you really don't need it to do it too much. If you really want to know about the view directions, I think you might want to render a lot, but it's quite fast.
Okay, and what do you think is the next thing after, say, addressing the speed issue? Where do you think is the next problem to solve in NeRF?
I think the next problem to learn is to really, how do you like learn a reusable, like you want NeRF to be reusable, or like reusable pieces in 3D or something like this, basically training across multiple scenes. And I know there are other couple of directions in this direction, and like, you know, but I think if you actually want to train on multiple scenes, I think it's actually quite important that you can actually train fast. And so hopefully this is why it's not just making it real time for the, you know, rendering purposes, but it will also actually help us do a lot more if you can train more scenes faster, do more learning-based approaches.
Right. And there's a question from Alexander Trevitic. Have you considered some extension which creates a PlenOctree in a single forward pass given some images?
Yeah, I guess, you know, so all of this, you have to actually, you know, go back to 2017. It's not even that old. 2000. A lot of work in voxels from 2017 to 2018, or to 2016 to 2019 actually is doing this, right? People used to directly predict voxels. I have to mention that Shubham Talsiani, who I think is talking next, has this work called DRC in CVPR 2017. And it really essentially does the volumetric integration on voxels. But back then we were like, oh, voxels, you have to store them directly. It's too much. And so we didn't really look into it. But basically what NeRF is doing is just like a continuous version of this. And so there's a lot of papers like that from back then that does this. I mean, which is what our Pixel NeRF was kind of inspired on. Actually, Shubham, and also there's a paper from Andreas Geiger's lab that actually predict the sparse octree representation from images. And so those things can be, I think, directly applied, actually. Would be interesting to see. Okay. And I want to answer a quick question, which is one of the persons asking, have you tried the training without the mask supervision? But this is NeRF, so there's no mask supervision used anywhere.
No, that was, I think, for the previous
that's the previous. I see. Okay, good.
And then I don't see any other questions. Well, thanks a lot then, Angjoo. And again, great presentation, good work.